And we're back. Welcome back and happy Thursday. Today, we will continue on a little bit more with the exponential distribution, and then we will pivot to the gamma distribution. But before we do so, a few administrative bits. The reading. By the 12th of November, please make sure you're staying up on the reading, pages 75 through 92 in the Barron text, covering sections 4.1 through 4.2.4. Including today, there are 6 class meetings left, and written exam number 2 will be administered Thursday, the 19th of November at 12 noon, and it will be for 30 hours, after which you will, or by which you will be submitting electronically through Blackboard. The residence halls will be closing Wednesday, the 25th. That's the day before Thanksgiving, and all students who are on campus will be leaving the residence halls by 5 p.m. on that day, only to come back next semester, the remainder of the semester after Thanksgiving towards the end of fall 2020 will be 100% online. The last day of classes will be the 3rd of December, the day after reading day, the 4th of December. Our scheduled final exam period for this course, Stochastic, will be Tuesday, the 8th of December, in the block of time from 10:30 a.m. to 12:30 in the afternoon. We'll be using that time for your final project presentations, and the last day of finals was when we'll have our final projects due, the report, the code, and experiments, and that will be the last day of finals, which is the 11th of December at 8 p.m. Okay, so let's continue. When we last left off, we talked about the exponential distribution, and we said it was a continuous distribution trafficking in the amount of time transpiring before you see the next occurrence of some event. And because time is uncountably infinite, this is a continuous distribution, and we talk about the density function. And so our density function, f of x, is lambda e to the minus lambda x for all times greater than 0. We had the cumulative distribution function, or CDF. Big F of x is 1 minus e to the minus lambda x, and we use calculus to solve for that. And we also use calculus to solve for the expectation, which is 1 upon lambda, and the variance, using the variance equation and integration by parts applied twice, we get variance of an exponential distribution is 1 upon lambda squared. Okay, and so let's take a look at another linkage between the exponential distribution and the Poisson distribution. And I'd like to stress that the exponential and the Poisson, they're related, but they are not the same. The Poisson is a discrete distribution, where the exponential is a continuous distribution. That's a really important distinction. And so we talked about the Poisson configuration, and in that we have a number of events that occur in standardized modules of observation, delta t, and the only requirement was these modules of observation had to be of a consistent size throughout time. And so we have the probability mass function for the Poisson here on the left. P of x is equal to e to the minus lambda, lambda to the x upon x factorial, where lambda was the rate parameter. And then for the exponential distribution, we had the density function, f of x is equal to lambda e to the minus lambda x for x greater than 0. And the CDF, cumulative distribution function, is 1 minus e to the minus lambda x. Likewise, when we solved for the expectation, mu, for the Poisson, we got lambda. When we solve for the expectation, mu, for the exponential, we get 1 upon lambda. We solve for the variance, sigma squared, for the Poisson, we get lambda. We solved for the variance for the exponential distribution, we get 1 upon lambda squared. Okay, and so why do we have that form that we do for the exponential distribution? We said our density function is lambda e to the minus lambda x. And so we're going to explore this a little bit and show another relationship between the exponential and the Poisson. And so we have the occurrence of some event in a Poisson configuration, and then we have some amount of time. That amount of time is governed by the exponential distribution, but that time is the time that transpires between events. And we use the word rare events because we're talking about time that transpires over some measurable amount, some significant amount or a good amount of time. And so this time I'm marking t, and the bounds of it is from where this arrow extends on the left-hand side to right before the right-hand side, right before that event. Now, of course, in the diagram, I leave a generous space because I want to be able to draw things to demonstrate. But this arrow really goes right up to that next occurrence of the event. And so we have this time, t, and that's the time before we have the next event. And then we have what comes after t. We say that region along the timeline is greater than t. And so one of the things that is key to our observation is because this is the time between or until we see the next occurrence of an event, you're guaranteed that, of course, during this t, many seconds or milliseconds or however long it is, we have 0 events that occur. Because if more than 0 events occurred within this t units of time, this would not be the time until the next event. It would be shorter than t. So by definition, within t, there's no occurrence of an event. And greater than t, at some point, we have the occurrence of an event. And so it's assured that on the real number line, within that period between 0 and t on the closed interval, where t is that same green arrow, that region t, there are 0 events that occur. And so if we were to think about this t as a rate, remember, when we talked about the Poisson configuration, we said this module of observation, delta t, does not matter. It could be 1 second, it could be 10 seconds, it could be 5 milliseconds, it doesn't matter. And so if we imagine this t, these green arrows, that region, as being a module of observation, if we look at the rate associated with that t, well, that would just be that lambda, that average across the Poisson configuration. We multiply by that time t, and the number of events we get, that's our effective rate during this period. That's what rate means. So our effective rate for events that occur within this period is lambda, the average rate across all of time, times t, this unit of time, this window, our module of observation between these 2 event occurrences. And so we can take this rate, lambda t, where that lambda is the lambda for the Poisson distribution, and we can plug that in to the probability mass function for the Poisson. We said the Poisson is e to the minus lambda, lambda to the x power upon x factorial. So here we're plugging in lambda t for our rate in the exponent of e, and we're plugging in lambda for the rate exponentiated to the x power. And so if we do that, well, and we evaluate for x equals 0, given that rate, we're evaluating this particular Poisson distribution, given that rate lambda t, we can evaluate it for 0, where that's the 0 occurrences within that window. And so in doing so, we're talking about what is the probability, given an average rate of lambda t, what is the probability that we're going to observe 0 events? Okay, well, plugging in 0, what do we get? We get e to the minus lambda t. Well, that looks a lot like the e to the minus lambda t for the exponential distribution. Well, it is. And so this is the time period in which 0 events occur. Okay, so there's that relationship between the exponential distribution and the Poisson. That exponential distribution, when considered from the perspective of the count of events from a Poisson, that e to the minus lambda t corresponds to the probability that we observe 0 events within that module of t many units of time. Okay, so this event that occurs, we know that this is the time until the next event. So for that period greater than t, that's from this green square going to the right, the event occurs within some time greater than that. Because by definition, if it's the time until the next event, well, after that time, we get that event. So an event occurs sometime greater than that t, where that t is what we're talking about for the exponential distribution. And so what we want then is that we want to compute or calculate or express the probability that the event occurs in some time that's greater than t. So that's what we're after here when we talk about the exponential distribution. we're dealing with the probability of an event occurring at some time greater than t. So let's take a general view of a probability density function. And this probability density function is defined from minus infinity all the way to positive infinity. Now let's imagine on the horizontal axis we have time, and then we're going to mark time t along the horizontal axis. And on the vertical axis, we have the probability associated with a particular event occurring. And so here we have the probability that you get an event after some time t corresponds to this region underneath the probability curve to the right of this t marked along the horizontal axis. So what we need and what we're going to enterprise to do is consider the area under this probability curve, and the area under this probability curve going from t to the right off to infinity, positive infinity. That's going to be the probability that you get an event after that time t. And so we know that the CDF, cumulative distribution function, capital F of x, is the antiderivative of the PDF. And we're going to use this idea of the antiderivative or integral to give us the solution for this shaded region. And that's what we're after. And so we know from the law of total probability, we say the probability that an event occurs in all time. Now, that's just the area under the curve from minus infinity to plus infinity. And the law of total probability tells us, well, for a continuous distribution, law of total probability holds, and that's just equal to 1. Okay. Well, now we want to subtract from that the probability that an event does not occur in time t. So that's that condition that we talked about from minus infinity up until t. And we can use the CDF to calculate that probability of the event not occurring in time t by looking at all of those times from minus infinity, and it's really 0 once you get less than 0. So it's really from 0 up to and including t. So we want this purple shaded region. So we start out with the green shaded region. That's law of total probability. We know it's 1. And we subtract from it the cumulative distribution function for t. And that gives us this green shaded region, the probability that the event occurred in a time greater than t. Okay, so that's what we want, the probability that the event occurred in any time minus the probability that the event did not occur or in some time less than t. And so this probability of the event occurring, well, if we consider from the Poisson, that's just 1, law of total probability. And if we subtract off the probability that the event didn't occur in time t, well, using that rate of lambda t, that's relating the Poisson, the events, the exponential distribution's time, that t units of time to the Poisson, that's a rate effectively of lambda t, and then we have 0 events in that time. So if we take that probability of the event not occurring in time less than t, translated into a Poisson, a count of events, probability mass function, we're going to subtract off that probability that we just calculated up above, e to the minus lambda t. And so if we do that, what we get is 1 minus e to the minus lambda t, which from before is exactly the cumulative distribution function of the exponential distribution. So the exponential distribution can be posed in terms of the Poisson by relating the rate to the time period and the count of events during that time period to what happens during that t many units of time, i.e. no event occurs. And we can come up with the CDF of the exponential directly from what we know about the Poisson, which traffics in counts, whereas exponential traffics in time. And so there's a deep relationship between the exponential distribution, which traffics in continuous quantities, time, and the Poisson distribution, which traffics in discrete quantities, namely counts of events. Okay, and so this is the time between events, and this is our exponential distribution. And so this exponential distribution has an interesting quality. It exhibits what's called the memoryless property. it doesn't matter how long you're waiting, how big that t is. Once the event occurs, you start the clock for how long you wait. You start it over from zero again. You reset the clock. And so what this says is the probability that t, the amount of time you wait, is greater than little t, some value, is equal to e to the minus lambda t. So the memoryless property says the probability of the time you wait being greater than t plus some extra amount x, given that the probability of time that you wait is greater than t, is equal to the probability of time you waited being greater than x. And what it says is that knowing that you've waited longer than little t, that little t doesn't matter. It's just that x that matters. And so it says once an event occurs, you reset, and all that matters is the amount extra that you're going to wait. So that's what this memoryless property means. Once you see an event occur, you start waiting again for the next occurrence from scratch. And so here, an event occurred at t, right after t. So any amount x that you wait, you start from zero, and that's just the probability of that event occurring after that x amount. Okay, and so let's go through a proof, and this is the high-level proof of the memoryless property. And we'll start out with our condition, probability of big T is greater than little t plus x, given that you know an event occurred after little t, is equal to, we'll just expand this in terms of our definition for conditional probability. Now remember, we said conditional probability says the probability of A given B is equal to the probability of A and B over the probability of B. Now, of course, this is an event. We'll call that event A. This is an event. We'll call that event B. So here's our A and B over the probability of B. So we're just expanding out here the definition of these temporal events given what we know about conditional probabilities. Okay, so now what we're going to do is going to take this intersection. So here's an event, and here's a timeline. And on this timeline, we have starting at 0, time goes to infinity, positive infinity. We have some event, and that event is going to be big T is greater than t plus x. So here's t, and here is x more than t, and we're going to call this point t plus x. So the event of interest, when we say t is greater than t plus x, we're going to talk about this region. Here's t plus x going off to the right. And we'll draw an open circle here to represent greater than. It doesn't include the endpoint. And then, so this is our event, t greater than little t plus x. Okay, so that's one event. Our next event, we have the same timeline going from 0 up through positive infinity. And this is the same little t. And this is going to be the event big T. There's a typo. That should be big T. Big T is greater than little t. That's the following interval. So open interval, not including little t, going off to the right. So if we were to take the intersection of these two events, what's common? What's common when we take the intersection between these two temporal events is this portion from t plus x going off to the right. And so if we rewrite this intersection, that's nothing more than the probability of t, big T, greater than t plus x over probability of t, big T, greater than little t. And so this intersection physically turns into just this quantity, t plus x, going off to infinity because of that intersection. All of the events between t and t plus x, well, they're not common to the first event and the second, but here that portion from t plus x off to infinity, they're common to both of them. So we rewrite that intersection as follows. All right, so now, of course, going back to what our original scheme was for the probability that t is greater than some time, we have e to the minus lambda times that time, right? And so it doesn't matter what that time is. We said that at the outset. That time could be t. That time could also be t plus x. If that time is t plus x, we're going to say e to the minus lambda, whatever that time is, t plus x. Okay, so we're going to take this expression, both in the numerator and the denominator, and we're going to write applying what we know for this probability when we solve for that using the Poisson distribution, plugging in for the exponential distribution's time between events. And we're going to plug in for the numerator, e to the minus lambda times t plus x. And we're going to plug in for the denominator, e to the minus lambda t. And so now, using some algebra, we're going to factor, and we're left with e to the minus lambda x. And there's our result. We notice that, hey, wait a minute, it doesn't matter if we have probability of t greater than t plus x given that an event occurred after t. We reset the clock, and we're only concerned about that amount x. That's the memoryless property, and there's our proof. Okay, so let's go on to a pivot, as it were, to the gamma distribution. And the gamma distribution also traffics in time. To motivate this, let's imagine you go to a website like Amazon.com and you're going to make a purchase. So the first step you're going to do is you're going to visit Amazon.com. And so you type in www.amazon.com on your browser, you bring up Amazon's web page, and it takes some amount of time for that web page to load. And that amount of time, it can change. It can be more, it can be less. It's stochastic, absolutely. So then you enter into a search field, a query for a product item. When you hit enter and enter in that search, it's going to take some time for that query to make it to Amazon's database in their cloud, and it's going to look up that item and give you back the search results and display it. Okay, so you enter in a search query and you hit enter. That's going to take some time to do, and then it goes to the server, and the database computes the result set from its database, and that's going to take some time and presents you back that list, and you click on something. When you click on something, step 4, you're going to select some item. It's going to take you some time to read that. Sometimes it might be fast, sometimes it might be slow. That is also stochastic. And then after you select it, you then enter in your credit card information to pay for that item. And so for a website purchase, you have a bunch of steps. Step 1, 2, 3, 4, 5, visit the page, enter the search query, get the result set, select an item, and pay for it. Each one of these items is independent from one another, and each item takes some amount of time that is stochastic. And so this type of stochasticity, I call the web purchase model, but it's really called algorithmic execution. You have two things. You have a bunch of steps. In this case, it's 5 steps. It could be 10 steps. It could be 2 steps. It doesn't matter how many steps it is, but it's some number of steps. Each step is independent from one another, meaning that one step's time that it took doesn't influence the other step's time. And moreover, are they independent, that each step takes some amount of time that is stochastic. So step 1 takes some time, step 2 takes some time, step 3, 4, 5 all take some time. And if you repeat this again, step 1 will take some amount of time, which isn't always the same as the first time you ran this algorithmic execution. And so the time for each step varies across customers, and you can define each step as the time between events. Traffic's in time, well, that's the exponential distribution. So the time it takes for each step, i.e. the end of a step to occur, or the beginning of the next step to transpire, well, each step takes some amount of time that you can describe as being an exponential distribution. So you have a sequence of steps, and let's call that size of the sequence alpha. So you have alpha many steps, each one of which takes an exponential distribution amount of time, and each step is independent. So this is called algorithmic execution, or so-called multi-stage execution. And so a multi-stage execution you model as a gamma distribution. You say your x is time, so it's a continuous distribution, time is uncountably infinite, but this time is different. This time is going to be a bunch of stages that proceed in some number of steps, each one of which can take some time, and it's stochastic. And so we say the gamma distribution, x is distributed as, and it's parameterized by 2 governing factors, alpha, which is the number of stages or steps, and then lambda, which is governing the time for the exponential distribution, governing those times for each of the steps. And so the density function for the gamma distribution is as follows. We say f of x is equal to lambda to the alpha power, and this symbol, that's gamma of a, where a is the number of stages, times x to the alpha minus 1 e to the minus lambda x. And so this e to the minus lambda x, that looks very, very exponential distribution-like. They are related. In fact, the gamma distribution is nothing more than a concatenation of a bunch of exponentials. But nonetheless, we have x, our time, is going to be greater than 0. Now, this gamma function is a kind of factorial in disguise. If you take an integer and you run the gamma function on some integer a, that's just a minus 1 quantity factorial. If a is a positive real number, we use the integral. That gamma function where a is a positive real number is just the integral from 0 to infinity, x to the a minus 1 e to the minus x dx. But we're going to focus only on a values for the gamma distribution where a is a positive integer. Okay. And so this is the density function for our gamma, and we have a definition for what the gamma function is, and the gamma distribution gets its name from the gamma function. And so since it is a continuous distribution and it has a density function, we need to know the CDF. Now, of course, the cumulative distribution function is nothing more than the integral from minus infinity up through some value, and we take our f of x dx. That should be an x, that's a typo. And we can't simplify this very easily. So we're going to use a little bit of a trick here in order to make this more easy to solve. And so we have our density function that we're going to integrate from 0 because it's undefined, 0 when it's less than 0, and our input. So our integral is going to go from, instead of negative infinity to some bound, we're going to go from negative infinity from 0 to x, rather. And so we're going to simplify this CDF for the gamma distribution. We know that when we take the integral from negative to positive infinity, law of total probability says that the integral for that density across all of the support values for that density over which it's defined, it's equal to 1. Law of total probability holds for density functions. Absolutely. And so we're going to use that result with our density function for the gamma distribution, and we're going to come up with an identity that's going to help us for all sorts of solutions for summary statistics. And so here is our law of total probability. We take the integral from minus infinity to positive infinity of our density function dx, and that's equal to 1. And we know that our density for the gamma, everywhere from minus infinity to 0, that density function is equal to 0. And so we're going to chop this up into two pieces, from minus infinity to 0 and from 0 to infinity, f of x dx, and we know that's equal to 1 because of our law of total probability. Well, this term is equal to 0, so we're going to say that infinite integral here is equal to 1. And so we plug in for our density function f of x, and when we do so, we get this expression. We have lambda to the alpha power, our integral from 0 to infinity of lambda to the alpha power upon gamma of alpha times x to the alpha minus 1 e to the minus lambda x dx. Okay, and so one of the things we observe is this integral is with respect to x dx, and we have this lambda to the alpha power upon gamma of alpha. Well, these two are constants, and we're going to factor this out underneath this integration, are constants. And so we factor that out, and we're left with that leading constant, lambda to the alpha power upon gamma of alpha, our infinite integral from 0 to infinity, x to the alpha minus 1 e to the minus lambda x dx is equal to 1. And so now we're going to multiply both sides of equality. We have this expression. On one side of equality, we have our integral. On the other side of equality, we have 1. So we're going to multiply both sides of equality by the same quantity. We're going to multiply by gamma of alpha over lambda to the alpha power. And so on the left-hand side, this leading coefficient is going to go to 1. On the right-hand side, we're going to get a gamma of alpha upon lambda to the alpha. Okay, so let's do that, and we get an expression that says gamma of alpha upon lambda to the alpha is equal to this integral. And so we're going to use that as an identity to make life easier for us when we're solving for other quantities for the gamma distribution. Okay, so one of the observations we're going to make, we're going to look for a pattern here. So every time we see this expression, our gamma of alpha upon lambda to the alpha, we notice that we have some x to some power. We multiply it by e to the minus lambda x. Now that power that x has is one less than this, what this parameter is for the gamma function and for this exponent. Well, this parameter is alpha and the exponent is also alpha. So wherever we have alpha on this expression, that's always going to be one more than the exponent on this x. So let's remember that pattern. Okay, so now if we want to compute our expectation for the gamma distribution, well, what is expectation? It's the probabilistic weighted sum. And we rewrite our identity just so that we'll remember it. And our expectation says, all right, our probabilistic weighted sum, we have the value x weighted by the density function dx over all the values from 0 to infinity. So now, okay, let's do this. Let's plug in what our density function is. We do that for f of x, and then we factor out this constant underneath this integral. And so this gives us lambda to the alpha power upon gamma of alpha, our integral from 0 to infinity, x, that's our value, and that's what remains from the density function, dx. So we have x times x to the alpha minus 1, e to the minus lambda x dx. And so now we multiply this x times the x to the alpha minus 1. That's just our leading coefficient, lambda to the alpha power upon gamma of alpha, our integral from 0 to infinity, x to the alpha, e to the minus lambda x dx. And so we take a look at this expression and we say, hey, wait a minute, that's exactly like our identity. And so we can substitute this expression where that substitution has an alpha that is one more than the exponent on x. So here the exponent on x is alpha, and so we're going to replace that with gamma of alpha plus 1 lambda to the alpha plus 1 power. And so we make that substitution, and this is what we have. We have gamma of alpha plus 1 over lambda to the alpha plus 1. Now, if we do this, well, we have that term for the left-hand side of this product, lambda to the alpha power over gamma of alpha. And then we have this other term, well, that denominator, the lambda to the alpha plus 1, that's the same as lambda to the alpha times lambda to the 1 power. And this gamma of alpha plus 1, well, alpha is a count of the number of stages. We said from before, this gamma rather, on an integer is just that integer minus 1 factorial. So that's nothing more than, well, alpha plus 1 minus 1 factorial. That's just the same as alpha minus 1 alpha factorial. And so that alpha factorial, if we were to expand that out, that's just alpha times alpha minus 1 times alpha minus 2, alpha minus 3, and so forth. That's alpha times alpha minus 1 factorial. Well, that alpha minus 1 factorial, that's the same as gamma of alpha. And so we can rewrite this expression. Well, that first term is lambda to the alpha over gamma of alpha. And this denominator becomes lambda to the alpha times lambda. And this numerator here, that's just alpha times gamma of alpha. And we're just calling this alpha minus 1 factorial. It's just gamma of alpha. And so if we look at this, all right, well, The lambda to the alpha in the numerator cancels with the lambda to the alpha in the denominator. The gamma of alpha in the denominator cancels with the gamma of alpha in the numerator. And we're left with alpha over gamma. Okay. And so we do this, and we're left with alpha over gamma, and that's our result for the expectation of a gamma random variable, and therefore for a gamma distribution. Okay, so now there's our expectation. We'll just note that down, and now we'll enterprise to solve for the variance for the gamma distribution. Now, instead of going the long way, we're going to use the variance equation. And that variance equation we did before when we talked about the exponential distribution. And that's variance of a gamma random variable x is equal to the expectation of x squared minus e of x quantity squared. Well, we know what e of x is. That's just alpha over lambda. So e of x squared is alpha squared over lambda squared. So now what remains is to compute e of x squared. Okay, so let's plug in for e of x squared. That's just x squared. So there's our x squared. And we multiply by the density function. Here's our density function. And so when we multiply by that density function, we have it times our lambda to the alpha upon gamma of alpha times our x to the alpha minus 1 e to the minus lambda x dx. And of course, we can factor out that leading coefficient out from underneath of the integration because it does not involve x. For all intents and purposes, it is a constant. And so we get this expression, and now we're going to do a little bit of algebra, right? Well, we know x squared times x to the alpha minus 1, the exponents add, so that's x to the alpha plus 1 power. And so we're left with this expression, and now we're going to make a substitution from the identity that we had before up here, right? And again, we look at the exponent for the x, and that exponent increment by 1 is going to be the parameter to the gamma, that's the alpha, and the exponent on the lambda in the denominator. Okay, so that means this expression, well, our x has an exponent of alpha plus 1, so we're going to rewrite this whole integral as gamma of alpha plus 2, because 1 more than alpha plus 1 is alpha plus 2, over lambda to the alpha plus 2. Okay, so we're going to make that substitution, and now we get the following expression. So now we're going to look at our definition for what the gamma function is. Well, gamma function of alpha plus 2 is equal to alpha plus 2 minus 1, so that's alpha plus 1 quantity factorial. Now, of course, alpha plus 1 quantity factorial is the same as alpha plus 1 times alpha minus 1 times alpha minus 2 minus 3, and so forth. So all the other terms starting with the alpha minus 1, we'll just call that alpha minus 1 factorial. And so we can rewrite this expression as just alpha, lambda to the alpha over gamma of alpha times, now this alpha plus 1 times alpha, and then that alpha minus 1 factorial, we can just call that gamma of alpha, the same thing. And in the denominator, we write lambda to the alpha times lambda squared. Okay, so if we look at this, we have a lambda to the alpha in the numerator, that cancels. Lambda to the alpha in the denominator, that cancels. We have a gamma of alpha in the denominator, that cancels with the gamma of alpha in the numerator. And so now we're left with alpha plus 1 times alpha over lambda squared. Okay, so if we do that, we have our alpha plus 1 times alpha over lambda squared. And that's going to be our e of x squared. But we're not done yet, because we did our substitution for e of x squared. That's our alpha plus 1 times alpha upon lambda squared. So that's our e of x squared. And then we had our e of x quantity squared. Our e of x was alpha over lambda. And so we're going to take that alpha over lambda, and we're going to square alpha over lambda. That's alpha squared over lambda squared. So they have a common denominator, and if we take this numerator and multiply out, that's just alpha squared plus alpha minus alpha squared over lambda squared, right? The alpha squared and minus alpha squared cancel. That's just equal to alpha over lambda squared. And there's our result for the variance of a gamma random variable, alpha upon lambda squared. Okay, so these are our summary statistics, and we used a result from total probability and the CDF in order to find an identity that we used for a pattern to then help us with a solution for expectation, and then we use the variance equation to solve for the variance. And so in closing, for a gamma distribution, the expectation is alpha upon lambda, where alpha is the number of stages and lambda governs the time. And the variance is alpha upon lambda squared, where the alpha, again, is number of stages and the lambda is governing the time. So with that, that's all I had to say for today. As usual, we'll end there. And please, as usual, stay on top of the reading, stay healthy, stay safe, and I'll see you all on Tuesday.